So we arrived at the following equation for phi of s. So with simple differentiation, you get the following thing. S phi prime prime plus phi prime and you can solve it, build their solution in terms of a contour integral following the standard procedure, p and q polynomials, and so on and so forth. So here's for your reference the polynomials. And as a result, you just integrate p over q, and you get the following z function and v function. So z function is as follows. And now, using this function, we build the exact solution in terms of the following integral. Now, as you remember, mu is positive, and the question is how to choose the correct contour placement for our solution. And to this end, we draw a complex plane of t. And we see that we deal with multivalued function, t2 mu and t plus 2 ik 2 mu. And we need to draw branch cards to define them in a single valued way. So it's up to us to choose the direction of the branch card. But keeping in mind that we are interested in specific plane wave asymptotic, it's almost obvious that both of the branch cards should be chosen pointing to the left in the complex plane. So, and here they are. The first one goes from branch point t equals 0 to minus infinity. And the second one starts at point minus 2ik and goes again to minus infinity. However, before we draw it, let's actually do the following thing. In fact, the convergence of the integral defining our solution depends on the sign of our s function. So s, as you remember, is proportional roughly to x, because s actually equals to x minus x1, where x1 is the position of the pole of our potential. So to get rid of this unsuitable dependence, let's introduce the change of variables. In fact, let's rescale our complex value t. So st now rescaled to t. And this changes the solution slightly. So now we have a simply exponent in our exponential function. And the structure of the integral basically stays unchanged, with the only difference that in the brackets we will get s, additional s, instead of 2ik. And naturally, we'll get a prefactor here, and the prefactor is s to, let me have a look at, 1 minus 2 mu. Right. And in this case, the integrals are convergent. The integral is convergent very well in their left semiplane of complex variable t. Right. So the second branch card again points to the left in the direction of the convergence of the integral. And now the choice of the contours. Well, since mu is positive, we see that our v function assumes identical values, namely zeros, when, for example, t is equal to 0 or minus 2ik, so when t is a branch point. Or t may tend to minus infinity, then it's also OK. And by the way, after this change of the variables, of course, our v function change is also rescaled. And it became up to some arbitrary constant, t to mu times t plus 2iks to mu times e to t. So let's choose, I don't know, two possible contours. One of the choices would be, of course, the contour, the simplest choices would be the contour starting at point t equals 0 and stretching to minus infinity. The other possible contour would be the one which, the finite one, which connects two branch points, say from minus 2iks to 0. And let's figure out which contour is suitable, or not suitable, but relevant for the solution of our problem. So for large S or X, we expect their transmitted wave. So let's draw our potential profile again. So what we expect to get is as follows. Our potential well vanishes at large values of x. So at large x, positive or negative ones, we expect that our scattered wave becomes a plane wave, e to I k x to the right. And to the left, there should be a combination of the plane wave, incident plane wave, and reflected plane wave. We are interested now in large and positive x, because the wave is simply just a transmitted wave. So somehow, our psi function should be reduced to just this simple exponential, e to iks. Let's see which of these contours correspond to this asymptotic behavior. Let's study the first contour, this one. So when you look at the integrand, you see that there is no saddle in the exponent of the exponential. As you probably your experience tells you, that means that the integral is defined by the vicinity of the branch point. And the branch point here is just t equals 0. So what we do, we expand the integrand near point t equals 0 and extract the answer. And the answer is almost obvious, because you see that these brackets are turned into what? So s is large. We are interested in the asymptotic for s much greater than 1. So we discard t term here. Why? Because the convergence of the integrand is defined by the value of t's of the order of 1. So the first term can be discarded. And the integral is reduced to a simple gamma function type thing multiplied by this factor and multiplied by the prefactor s to 1 minus 2 mu. As a result, we get the asymptotic behavior s to 1 minus 2 mu plus 1 minus mu. So s to minus mu times gamma function of mu. That's it. So when you plug in this asymptotics into the initial ansatz, you get precisely the needed asymptotic behavior. Psi behaves as, so s minus mu cancels s to mu, and you get a simple plane wave. So this contour is correct. The second one, which is finite, will bring you a different solution, and it will be your homework to analyze the behavior of the solution at large values of s. This is not the finite one is not the right contour. Right. So let's analyze the behavior of our contour integral defining our wave function at large and negative values of s. And our intuition tells us that somehow there should some drastic change in their contour should take place. So сейчас, секунду, это придется этот момент вырезать полностью. Сейчас я повторю. So we expect that apart from their incident wave asymptotics, there also arise a reflected asymptotics, which should be, of course, proportional to e to minus I ks. So let's see how this comes about. Well, first thing we should keep in mind is that somehow we should go from large positive value of s to large negative values of s. And as we did many times before, the best way to do this is to go along the contour in the complex plane of s or x. So there are two choices: the upper semicircle of big radius or the lower semicircle. Let's analyze what's going to happen if we go from large positive s to large negative s along the upper semicircle. So now our s becomes a complex parameter. It's turned into s modulus s times e to I phi, where phi changes from 0 to pi in the counterclockwise direction. So that means that our branch point here will start to move in their counterclockwise direction, actually this direction, until it arrives at this upper point. So it rotates by pi. This is quite a peculiar situation because it will draw the branch cut with it, but the topology of their this Riemann sheet should not be changed. For example, if the branch cut, initial position of the branch cut was below their upper one, then it should stay as so even after this rotation. So after this transformation, our branch cut would look as follows. It will start here at the new position of point minus 2 IKS, and it will continue like that. So there is indeed a drastic change in the structure of the complex plane. However, that kind of deformation doesn't affect their solution, our solution itself, because it's still defined by the same kind of contour, and the shape is not changed. That means that if we go in the complex plane from large positive to large negative s along the upper semicircle, then our incident wave will turn into again an incident wave. There will be no reflection whatsoever. And the only outcome is that we should rotate in the counterclockwise direction. And this is basically our only choice, our only chance to get the reflected wave. So let's see what's going to happen now. So if I rotate this way in the lower semiplane, so it's a clockwise direction, that means that this point now will rotate like that. And here something interesting happens, because at this point when it rotates by pi by 2, it crosses actually the upper branch cut, but it's not possible. So in order to avoid this collision, the upper branch cut should also bend. And let me redraw this picture to show you what's actually going to happen. Well, here I redrew the picture, and now you see how the motion of the lower branch cut actually bent the upper branch cut. And finally, we see that something is going to happen with our solution, which represent our incident wave. We know that the steepest descent direction, which defines our asymptotic behavior, is actually this. It points to the left. So if we want to extract the asymptotic from that kind of bent contour, we want to bend it even more. So initially, it should point in this left direction. So it should go like this. Then, and the branch cut should obey this steepest descent direction. And then it should return and to circle around the upper branch cut, and finally go to minus infinity. And let's see how this deformation actually shapes the final reflected wave.